The objective then affine transformation. Geometric objects go through a transformation stage before being rendered. A general family of geometric transformation commonly used in computer graphics is called affine transformation. Affine transformation maps parallel lines to parallel lines, which mean transform preserve the parallel line. The affine transformation that also preserve the distances beside the parallel lines are called isometries. Or also it can be called Euclidean motions or rigid motions. Common affine transformation is the translation, rotation, reflection, scale, and shear. We will talk about each kind of this transformation. First, for the translation. A translation moves all points of the object by a fixed amount, as we can see here, along the x and the y. So it is specified by the amount of movement in the x and y direction. A translation is isometry because besides it's an affine transformation, it is also isometry since it does not change the length of the sides and the angles between the sides. This picture shows a translation of three steps along the x-axis and -1 step along y-axis, which means it moves 3 units to the right and 1 unit upward. Then this is the initial square, and this is the square after the translation. So now for rotation. A rotation rotates the object around a point by an angle. It is determined by the point and the angle. A rotation is also an isometry since it does not change the orientation, does not change the distances and the angles inside the shape. It only changes the orientation of the shape. The following figure shows a rotation of 45 degrees about the origin. Now for the reflection. The reflection maps the object to its mirror image about the line. A reflection is also an isometry. It only changes the orientation of an angle. It preserves the distances and the angles between the sides. This image shows a reflection about a 45 degree line between the x and y axis. As we can see, the transformed square is an image of the initial square with respect to the 45 degree line. Now for scaling. Scaling resizes the object by a certain fixed factor in the x and y direction. Scaling is not an isometry because, as we can see, it changes the distances and angles. However, it preserves parallelism. The following figure shows a scaling by factor 1.5 and 2. Then each side or each point coordinate will multiplied by 1.5. If we take this point, the coordinate of this point is 1, 1. The x coordinate will be multiplied by 1.5. Then the x coordinate of the new point is at 1.5. And the y coordinate is also 1 multiplied by 2. Since the scaling along y is 2, then the point is at 2. If we see for this point also, 2 is multiplied by 1.5, which is 3. As we can see here, this is the point, the transformation of this point is this point. This is a 3, and the y coordinate of 2 multiplied by 2, then it is formed. As we can see, the transformed shape will be as the initial with a scaling factor, which is 1.5 along x and 2 along y. Now the shearing. A shearing about a line shifts a point by an amount proportional to the signed distance to the line, as we can see in this figure. The movement of the points are parallel to the line. Points on the line are moved. Points on the line are not moved. Points on the opposite sides of the line are moved in opposite direction, as we can see in this figure. A shearing is not an isometry since it doesn't preserve angles and the length of side. It only preserves parallelism. The following figure show a shearing by the factor 1 along the horizontal line y equals to. Mathematically, a 2D affine transform can be represented by 3 by 3 matrix. An affine transform require 3 by 3 instead 2 by 2 matrix, because transforms such as translations are not linear in a 2D space. Using the concept of homogeneous coordinate, it is possible to treat all affine transforms in a linear framework by adding one dimension to the vector representation of the point. Now, for a basic transform, it is usually easy to find the transformation matrix directly. For a rotation of angle theta about the origin, the following matrix represents the rotation of angle theta: cosine theta sine theta 0 minus sine theta cosine theta 0 0 0 1. Always the third row in the matrix will be 0 0 1. Here we see a translation by A and B, A along the x direction, and the B is the translation along the y direction. The matrix is 1 0 A 0 1 B, and like the previous, the third row is 0 0 1. Now for the scaling by factor alpha beta, has the matrix alpha 0 along x alpha and beta along y, 0 0 0 beta 0, and along z 0 0 1. A reflection about the line y equal kx is also represented by the following matrix, where k is the slope of the straight line. This is the matrix for a line passing through the origin. If we have a line, for example, we want to make a reflection about a line of the form y equal kx plus b, then we can make a transformation y minus b equal kx. Then we try to make translation, and then by factor b, and then may apply the reflection about line equal kx. A shear along the x-axis by a factor s is given by 1 as 0 0 1 0 0 0 1. The affine transformation matrix. The affine transform class allows a scaling with negative factors. The reflection can also be defined as a kind of scaling transform set to scale -1 1. An affine transform object can be used for both object transformation and viewing transformation. Shape create transform shape shape shape, and void transform point to the source and point to the destination. The create transform shape method transform and in an entire shape. The transform method performs the transformation on a set of points. The viewing transformation can be realized with the transformation in graphic 2D object. The graphic 2D object has the following method to manipulate transformations, which is the set transform affine transform tx and transform affine transform tx. The method set transform replaces the current transformation with the given affine transform object. The method transform concatenates the current transformation with the given affine transform object on the right. Example illustrate the effect of rotation on a rectangle. First, as before, we create an affine transform affine transform. Then we try to set a tx a rotation tx of by pi by 6 using method of pi over 6. We create the same rectangle as before, and then we try to translate the rectangle to position 50-50, and then we draw the rectangle. After this, we try to apply tx on the rectangle. After applying tx on the rectangle, the shape will be the rectangle will be rotated, and the rotated rectangle is named shape 2 until we try to draw the rotated rectangle above the origin, which is by an angle pi over 6. Here in this example, we will illustrate the scale. We try to make a scale by 2 along the x-axis and a scale by 5 along the y-axis. So first we create the transform shape tx, and then we set tx to scale 2 by on the x-axis and 5 along the y-axis. Draw the initial rectangle and apply the scale to transformation to the rect shape, and then we try to draw the rect shape. Here all the coordinates, the 4 coordinates are multiplied by 2 along the x-axis and 5 along the y-axis. We didn't see the whole transformed rectangle since it is out of the boundary of the graphic. Here we will see the shearing by 1 along x and 0 along y. As we can see here, we draw a rectangle, and we the initial rectangle, and then we apply shearing on the transformed shape, and then we try to draw it. As we can see here is the shearing about in the x direction by composition of transform. Transformations can be combined to form new transformations. For example, you may apply translation followed by a rotation and followed by another translation. Any composition of affine transform is still an affine transform. Any composition of rigid motion is still a rigid motion. Conversely, a transform may be decomposed into a series of simpler transforms. The transformation matrix of composite transform is the product of matrices of individual transforms. For example, if M1, M2, and M3 are the matrices for the affine transform, T1, T2, T3 respectively, Then the matrix for the composition C1 round, C2 round, C3 is M1, M2, M3. Note that the operation of transform composition is not commutative, so the order of applying the transforms is significant. In our notation, the transforms is a composite through the applied from right to left. For example, when the composite transform C1 round C2 round C3 is applied to point P, the order of transforms is C3, C1, C2 as follows. As we can see, we apply C3 on P, then C2, then C1. So composite transforms are useful in constructing complex transformations from simpler ones. If we need a rotation, for example, about a point 34 by 30 degree, we may first perform a translation to move the point 34 to the origin. Then we may perform a 30 rotation about the origin, and finally we can translate the object back to the point 34. Combining the three transforms, we may obtain the required transform. In this example, we have three matrices. The matrix first is the translation by -3, -4, then a rotation, and at last a third. So in a matrix combination, the four transform will be in the opposite order. First we have the translation by 3, 4, then rotation by the angle pi by 6, which is 30 degrees, and we use the matrix in the previous slide to determine the rotation matrix. And here is the translation matrix by -3 along x and -4 along y. In Java 2D, the Affine Transform class provides this method to support composite transform. First, we have the rotate. The rotate along angle theta, rotate angle theta along the point x, y, scale, shear, translate. Unlike the set2 method introduced in the previous slide, these methods don't clear the existing transform in the current object, but combine the current transform with the newly specified transform. The new transforms are appended to the right of the current one. So instead of simple transformation listed above, it is possible to combine the current transform with another affine transform object like concatenate and pre-concatenate. The first method is concatenate. It concatenates the other transform to the right of the current, while the pre-concatenate it concatenates the other transform to the left of the current. The order of transform composition is from left to right, and the methods above, except for pre-concatenate, concatenate the transform from the right. If we create a composite transform by calling the above method, the transforms are applied in the opposite order of our calling sequence. For example, consider the following code. Affine transform equal new transform dot rotate math dot pi over 3, transform dot scale to 0.3, and transform dot translate 100 200. The first transform to be applied is the translation, which is translation by 100 200. Then the second transform is the scale, and the third one is the rotate. So as we said before, the applied transform will be in the opposite direction. Composition example. The following example illustrates the use of transform composition. To rotate an ellipse about its center that is not located at the origin, you may first translate the object to the origin, then rotate around the origin, and finally translate the center of the rotated ellipse to its original point. So first we create the ellipse at 300 200 and of width 200 and length 100. Then we set the color to 160 160 160, and then we draw and fill the ellipse. Then we create an affine transform, and then we apply the translate of minus 400 minus 200. Then after that we assign the transform on the shape E, and we named it E, the new shape. Then we change the color and try to fill the translated ellipse. After that we change the color to black, and we try to draw the lines as an axis for the ellipse to see the rotation about the indicated point, which is 300 200. Then which is minus 400 200 out 400 250. Then we create we make a rotation of pi by 6, and we determine or we set the transform, which is the rotation on E, and we have a new shape E. And then we change the color, and then we make a translation by 400 250 to return the ellipse to its initial place. And then we apply the transformation of E, and we draw the E with the black color, which is 0 0 0. First, if we ask why we use the coordinate minus 400 minus 250, as we see that the upper corner of the ellipse is at 300 200. So if we want to translate the ellipse to the origin, which means the center to the ellipse will be the origin, then the center of the ellipse will move by half of the dimension of the length, which is 200, then 100 plus 300 to make the center at the origin, and half the length, which is 100, which is 50, plus 200. Then we make translation of the center to the y-axis to the center also. We see the output of the previous code. The program shows a shape at different stages of composite transformation. The shape is originally constructed with a bounding rectangle 300 200 200 100. So its center is located at 400 250. The objective is to rotate the ellipse by 30 degrees around the center, which is 400 250. To achieve this transformation, a composition of three transformation is used. First, a translation of minus 400 minus 250 will move the ellipse to the center. Then a rotation around the origin by 30 degrees. Then the ellipse is rotated and is still centered at the origin. Finally, a translation of 400 250 move the ellipse back so that its center is again at 400 250. The composition of the three transformation is the desired transformation. So to show all the parts of the figure, a viewing transformation is used to move the origin of the word space from the upper corner of the screen to 100 100. The x-axis and the y-axis are drawn to show the new origin. The ellipse at each stage of the transformation is displayed with different gray level. The rotated ellipse are not filled as it is indicated in the code.